Welcome back. Today we're diving deep into perimeter efficient fine tuning or PEFT techniques that let you adapt large models with minimal trainable parameters.
PEFT has become incredibly important because it makes fine tuning accessible even for large models that would otherwise require enormous computational resources.
Let's start with the fundamental motivation. Why do we need perimeter efficient methods?
Full fine tuning of a model with billions of parameters requires storing gradients and optimizer states for all those parameters.
For a 7 billion parameter model, with adding Nelly optimizer, you need roughly 12 bytes per parameter for optimizer states plus the model weights themselves.
That's around 84 GB just for optimizer states, plus more for gradients and activations. This quickly exceeds consumer GPU memory.
Fact methods reduce this by only training a tiny fraction of parameters, often 0.1% to 1% of the total.
This dramatically reduces memory requirements, speeds up training, and makes it possible to fine tune large models on modest hardware.
Let's talk about the first major fact approach adapter modules.
Adapters are small neural network layers inserted into the pre trained model, typically after the attention and feed forward layers.
The original model parameters are frozen, only the adapter parameters are trained.
A typical adapter has a bottleneck architecture. It projects down from the model dimension to a much smaller dimension, applies a nonlinearity, then projects back up.
For example, in a model with 768 dimensional hidden states, the adapter might project down to 64 dimensions.
This means each adapter has roughly 2 times 768 times 64 parameters, or about 100,000 parameters per adapter.
With adapters in each layer, you might train only a few million parameters total versus billions in full fine tuning.
Adapters also have a nice property. You can train different adapters for different tasks and swap them easily.
The base model stays the same and you just load different adapter weights for different applications.
Now let's talk about the most popular PEFT method, LoRa, which stands for low rank adaptation.
LoRa is based on the insight that the updates to weight matrices during fine tuning are often low rank.
Instead of updating the full weight matrix W, LoRa represents the update as a product of two low rank matrices WW-CAS, WNT-KAB.
Matrix A has shape D by R and matrix B has shape R by D, where R is much smaller than D.
This means instead of d squared parameters for the update, you only have 2 times d times r parameters.
For a 496 by 496 weight matrix with rank 8, you go from 16 million parameters to about 65,000, a 250x reduction.
LoRa typically applies to the attention weight matrices, the query key value and output projections.
During training, the original weights W stay frozen. Only the low rank matrices A and B are trained.
During inference, you can actually merge the LoRa weights into the base weights, so there's no inference overhead.
LoRa is extremely popular because it's simple, effective, and very memory efficient.
QLoRa takes this further by combining LoRa with quantization.
The base model is loaded in 4-bit precision, dramatically reducing memory usage.
The LoRa adapters are still trained in higher precision, but the overall memory footprint is small enough to fine tune 65 billion parameter models on a single consumer GPU.
Let's talk about prompt tuning and prefix tuning.
Instead of adding parameters to the model architecture, these methods add trainable parameters to the input.
Prompt tuning prepends trainable embeddings to the input sequence.
These aren't discrete tokens with a semantic meaning, they are continuous vectors in the embedding space.
The model learns to condition on these soft prompts to produce task specific behavior.
Prefix tuning extends this idea by adding trainable vectors to the key and value projections in every attention layer.
This gives the model task specific context at every layer, not just the input.
Prompt and prefix tuning are extremely parameter efficient. You might train only a few thousand parameters.
The trade off is that they typically require more training data and might not match the performance of larger PEFT methods.
Another PEFT variant is p-tuning, which uses a small neural network to generate the soft prompts rather than learning them directly.
This can help with optimization and generalization.
Let's discuss IA3, which stands for Infuse Adapter by inhibiting and amplifying inner activations.
IA3 modifies activations using learned rescaling vectors.
It multiplies activations in the attention and feed forward layers by learned scalar vectors.
This is even more parameter efficient than LoRa. You only add one learned parameter per hidden dimension per modified layer.
But it requires careful tuning to work well.
Another approach is bitfit, which only trains the bias terms in the model while freezing all other parameters.
Surprisingly, just training biases can achieve reasonable performance on some tasks.
Though it's generally less effective than methods like LoRa or adapters.
Let's talk about combining PEP methods.
You can use multiple PEP techniques simultaneously, for example, LoRa plus adapters.
Or you can stack adapters from different tasks to combine their capabilities.
There's also research into learning which PEP modules to activate for different inputs, dynamic parameter efficient tuning.
Now, how do you choose PEP hyperparameters?
For LoRa, the key hyperparameter is the rank R. Higher rank means more parameters and expressiveness but less efficiency.
Typical ranks range from 4 to 64. The optimal rank depends on the task complexity and how different it is from the pre-training task.
You also choose which layers to apply LoRa to. Applying to all attention matrices works well, but you can save parameters by applying to fewer.
For adapters, the bottleneck dimension is the key hyperparameter.
Common values are 64, 128, or 256 for models with dimensions in the thousands.
For prompt tuning, you choose the number of soft prompt tokens.
This might range from 10 to 100 tokens depending on the task.
Let's discuss the performance of PEP methods compared to full fine-tuning.
On many tasks, PEP methods like LoRa achieve 95 to 99% of full fine-tuning performance with 1% or less of the trainable parameters.
For some tasks, especially those similar to pre-training, PEP can even match or exceed full fine-tuning.
But on very different or complex tasks, full fine-tuning might still have an edge.
There's also variation across methods. LoRa tends to be more robust than prompt tuning, which can be sensitive to initialization.
One advantage of PEP beyond efficiency is modularity.
You can maintain one base model and many PEP modules for different tasks, domains, or languages.
Switching between tasks is just a matter of loading different PEP weights.
This is much more practical than maintaining separate full fine-tuned models for each task.
PEP also tends to have better generalization in low data settings.
When you have limited training data, updating billions of parameters leads to overfitting. PEP's parameter constraints act as regularity.
Let's talk about composing PEP modules.
You can train separate LoRa or adapter modules for different skills or tasks, then combine them at inference time.
For example, one module for medical knowledge, another for conversational style.
Composition can be as simple as summing the weight updates or using learned mixing weights.
This enables modular capability building, separately train different competencies and mix them as needed.
Finally, let's discuss the future of PEPT. There's ongoing research into even more efficient methods, better ways to select which parameters to train, and automatic rank or dimension selection. There's also work on PEPT for other modalities, adapting vision language models or speech models efficiently.
And research into whether PEP modules can capture the same diversity of behaviors as full fine tuning.
So, to recap, PEPT methods like adapters, LoRa, and prompt tuning enable fine tuning large models with minimal trainable parameters. They achieve competitive performance with far less memory and compute. They enable modular task adaptation and composition, and they're particularly valuable in low data regimes.
Next episode, we're exploring zero shot, few shot, and instruction tuning, different ways models learn to perform new tasks.
Thanks for listening. Until next time, keep learning and stay curious about